Hello, welcome everyone to this first webinar on future threads. My name is Allison Okamura and I'm the moderator, and I'm going to spend a few minutes on a quick introduction before I introduce our panelists, have them each give you some of their opinions, and then we'll go on to Q&A. So the purpose of this webinar series is to explore grand challenges for assistive fabric-based wearable devices across a number of domains. And this includes movement assistance, training, worker safety, sports, space exploration, and other high performance environments. And this is a pretty challenging goal that the genesis is that a group of researchers at some different universities got together and wanted to just discuss this idea of these next generation of fabrics that don't really exist yet. And so we thought we'd put together this webinar series to bring together experts from all over the country and the world, people from academia, people from industry, to have discussions. Tell us what are the important applications, what are the challenges, what are the considerations that we need to bring into place, and also maybe something about their own technologies and discoveries that can provide a good basis for how we move forward with this problem. So we're going to have these thought leaders and stakeholders explore the potential for these advanced textiles and fabrics that could maybe be used to revolutionize wearables in the future. And this is the first of what we're planning for probably 3 webinars in the series. We have one today, April 11th, that is going to be more focused on the topic of rehabilitation and assistance, perhaps aging in place for older adults in the home and those kinds of applications. The second webinar, which is happening next Friday, April 18th, is going to be focused more on applications related to the future of work. So physical labor, accomplishing skilled tasks, and how these wearables might help in those domains. And then the last event will be on April 25th, the following Friday after that. And that one we're going to focus more on sports, extreme levels of performance, and special skills related to body movement. But I'm going to begin with this group. Let me do a quick introduction in a slide of who our speakers are, and then I'll give a little bit longer introduction of each speaker, and they'll give a short 5-minute presentation with or without slides, whatever you all prefer. And then we'll go to some Q&A. First, I have some prepared questions, and then we'll be able to take questions from the audience. So if you're watching live online, there should be a link that you can click on to pose your question for the panelists. And then myself, along with my colleague Xiaobo Tan from Michigan State University, will help us pick out some questions that we will pass on to the speakers. So if I can just get this showing, give me a second. I'm just going to share this one slide to quickly introduce this topic. So we're calling this webinar series Future Threads, and this is the first one, Pioneering Assistive Fabrics for Movement Training and Performance. I'm the moderator. As I said, I'm Allison Okamura. I'm a professor in mechanical engineering at Stanford University, a member of our Stanford Robotics Center, and I have some varied interests. I'm an executive committee member of our Neurosciences Institute and also a science fellow at the Hoover Institution, among other things. Our speakers in order will be Paolo Bonato, Catherine Zeeland, James Cotton, David Rinkensmeyer, and Connor Walsh. And I am going to stop sharing this slide. And while Paulo prepares to speak, I'll just give him a little bit longer introduction. So Paulo will go first. He is the director of the Motion Analysis Laboratory at the Spaulding Rehabilitation Hospital in Boston. He's also an associate professor in the Department of PM&R at Harvard Medical School and an adjunct professor of biomedical engineering at MGH Institute of Health Professions at Harvard Medical School. And he has extensive experience in rehab technology with a special emphasis on wearable technology and robotics. And Paul, we're really excited to hear your 5 minutes. Please try to keep yourself to time yeah, introduce us to this topic and what's important to you.
Thank you to the organizers of this meeting. I'll keep it really, really short. I'm actually hoping that's going to be less than 5 minutes so that we have a bit more time for discussions. And I thought because James and I are the two from rehab hospitals, right? So that it was good for me just to tell the audience what we are really interested into. And I'll mention work by others, including folks in the panel. But I wanted just to make really a couple of quick points, right? And so, because in the title, we're using the term in the title of the event of the webinar, right? We're using the term assistive. And I just wanted to start with sort of that distinction to begin with, right? So in rehab medicine, we're really interested in both assisting and improving mobility in individuals and assisting the performance of movements, as well as retraining it. And those actually require really completely different designs. So I wanted just to mention this work, for instance, in which we took a technology that's a traditional exoskeleton technology, is not fabric-based, right? And so it's not an exosuits like the work that Connor has pioneered, right, and others on the call here. But it is a traditional technology. And this is technology that patients would use as an assisted technology so that it augments their mobility, but doesn't actually retrain their motor function. There are technologies instead, like the one that Connor, in fact, the pioneer, right? And that translated into commercially available product, which, thanks to the leadership of Lou Awad, the Boston University, a close collaborator of Connor, and our collaborations with them here at Spalding, we had the opportunity to test together with some of our colleagues, for instance, the Shirley Ryan Ability Lab and other clinical sites, right? And so, but this is technology that we have looked into, not just for assistive purposes, but also for retraining purposes. So what does it mean? It means that we're providing patients with this technology, and there is an expectation that not only this is going to augment their motor abilities, but they're actually going to retrain their gait so that as you remove the technology, if you will, right? And so the gait patterns actually have improved in response to the intervention. One aspect of it that my group has been a bit obsessed with, and others on the call, so I trust that, for instance, David Rankes-Meyer will have comments on this, right? So is that as we are looking to this technology in the past, we have not paid enough attention to how patients are actually responding to the interaction forces that we're generating with these technologies, irrespective of whether this is done with a very traditional technology, like the one that you see on the screen. This is a stationary, what I call a stationary robot. It's a Locomat Biocoma in Switzerland, right, which is very broadly used in the clinic. Or if you have a fabric-based systems, right, it really doesn't matter. You are generating towards the joints. What does happen in terms of retraining motor function and assistive motor function? If you're looking into assistive motor function, you're looking into a lot of redistribution within the anatomy. In certain cases, this is actually fundamental because you're trying to protect certain components of the anatomies and unload those components. That typically happens in orthopedic conditions. In neurological conditions, you're looking into how the patient is actually responding to the interactions. And we've done it over the past almost 10 years now by looking at motor adaptations. And we have combined that with the use of muscle synergies in order to assess how the patient is responsive. So that's point number one that I wanted to make, and hopefully that is going to lead to a good discussion. Point number two that I wanted to bring up is the fundamental role, in my opinion, of monitoring the impact of these technologies in the field, right? And so the first three slides, I only have 5 slides total. So this are my last 2 slides, Sally. So, right? So the first, these 3 slides are mobility, what happens with robotics that affects lower limbs, right? So you can do the same, of course, with upper limbs, right? So, but you need to have a grasp, no pun intended, on the effects of the interventions in real life. Dave Rankesmeyer has done fantastic work in this area. Another person that has done really interesting work for upper limb assessments is Catherine Lang, an occupational therapist who's very well known in the field. And she's done something relatively simple from a technical point of view, put essentially strap activity monitors, if you will, upper limb activity monitors on the upper limbs and look into ways to quantify the activities performed by stroke survivors during in the field, right? So during the day, by capturing the activity performed by the paretic limb, the contralateral limb. These are plots that she's generating on the basis of raw accelerometer data collected by these units. Essentially, the dots that kind of fall on the right side of each plot. If this task is performed with the paretic limb, the dot is going to fall on the left side. If the task is performed with the contralateral, it's in between. If the task is bimanual, and the vertical axis represents the magnitude, so how vigorous the movement is, and the color plot, essentially color code, gives you the third dimension, which is the number of instances in which you had that combination, which is very important when you look into recovering, improving motor functions in stroke. And when you do that with technology, you can also close the loop. This is a project that we ran thanks to NIH SBIR funding with a local company, a spin-off of Northeastern University. And we have used the technology not only to monitor, but also to encourage the use of the stroke-affected limb in these patients. So that's my second point is that what do we do when we deploy this technology? How do we monitor? And irrespective of whether it's purely sensing technology or a combination of sensing technology and soft exoskeletons, are we integrating the soft exoskeleton component right into a behavioral intervention? Thank you.
Terrific. Thanks so much, Paolo. We're going to go to Catherine Zeeland next. Catherine's the founder and CEO of Skip, which is the first e-bike for walking. It's an ultralight exoskeleton that could be a beautiful, intuitive, and transformative product that could help a billion people be more active and healthy. Catherine has a background in theoretical physics, and she's invented numerous patents and previously led early stage projects at Google X before she developed the underlying tech for what would eventually spin out to become Skip. Catherine, looking forward to hearing from you.
Thanks, Alison. I was going to skip the slides because I think what's actually most interesting is maybe the story about how I started getting into this field and thinking about soft actuators. Because I don't come from a robotics background, right? So, I started at Google X, which is all about finding the next moonshot technology. And so we were really interested in supporting, older adults, kind of aging populations with what could be an everyday consumer product. And so that's, probably a slightly different category to some of the more medical and rehabilitation work. We were really interested in something that, like my parents, like sort of average people in their 70s and 80s could purchase, use at home, and kind of be part of daily life. And I think coming at it from the outside, there's lots of appealing things about soft actuators in particular, or kind of smart fabrics, etc. The biggest one is around aesthetics, right? So the number one thing we run into is like, most people don't want to look like they're wearing a robot. We might enjoy that aesthetic because we're kind of from that field. But the average person, they're quite self-conscious, and especially they might be struggling with their mobility. They're even less likely to want to wear something that maybe either looks weird or looks like a medical product. It can be a point of stigma for people, unfortunately, like I wish it wasn't, but this is one of the biggest concerns we hear. And this is, again, especially true for our users. I think by the time someone has a very severe mobility impairment, they're so delighted to have any assistance that they might have a sort of higher threshold for what they're willing to wear. But for a lot of people who are just at that kind of struggle point, the dream would be something that just looks like an ordinary pair of jeans or trousers or an upper body garment, but can achieve the kind of assistance that we want, right? And so that's where soft actuators are very appealing. And so, you know, this was now a couple of years ago, but when we were at X, we looked at a huge range of soft actuators. So everything from, you know, some of the thermal polymers to twisted strings to Bowden cables to some of the kind of electrohydraulic actuators on the market. And there were lots of things that were interesting, but at the end of the day, like nothing that we felt was practical now to be a consumer product, which is not to say there aren't things that I think are interesting in the next 5 to 10 years. But that was a combination of, it was hard to get the usefulness, right? So like, yes, we want something that's low profile and could look like an item of clothing, but if it can only do a couple of Newton meters, that's not enough for the average person to find noticeable, right? So if someone's not going to put on a product if they're not noticing the amount of assistance it's giving us. And so when we put in requirements for, you know, okay, it has to do X many Newtons or have a stroke length of this much, that really starts to narrow the field of what's practical. The second constraint was around bandwidth and controllability. So especially for people who maybe struggle with movement or have balance issues and want to use this in a home setting, we want to be able to do precise control, right? Like if someone is starting to kind of get a little bit wobbly, we want to notice that and immediately pull them back. And again, some of the kind of more thermal mechanisms just aren't quick enough, right? So they don't have the kind of responsiveness that we'd look for to do precise control. And then the final thing was manufacturability, right? So, you know, the one we went the deepest down were things like electrohydraulic actuators, because in principle, they had the characteristics we were looking for, but there was no one making them, right? And again, what I'm hoping to do is a consumer product at scale, right? Like what's something that people can actually buy in the near future. And there was no suppliers, no manufacturing set up for that. And I think in one way that's a big gap for a lot of these technologies, is they're getting to the point where there's really proven, you know, techniques and promise coming out of a lot of my colleagues on the call here. But the jump is going to be, okay, but can we do that in a kind of cost competitive environment with some of the alternatives? And so having done all of this work and, you know, arguably invested a year of our life that we'll never get back, we ended up going back to users and talking to them about what really matters. And it's interesting because a lot of our assumptions were wrong. And so, you know, we'd said, oh, like we want these smart garment soft actuators so we can have this aesthetic of looking like a pant. And we thought it'd be more comfortable. People really care about comfort. But what's interesting is that is less, like they don't care about how the force is generated, right? And so what we've ended up with is a solution where we use essentially traditional actuators, right? Electromagnetic motors with some, you know, some custom sort of transmissions, et cetera, but pretty traditional motor technology. But as long as the force that they feel on their body is comfortable, they care a lot less whether the force is generated in a motor or in a soft actuator. And so that's kind of the transition that we went through. And so we still spend a lot of time thinking about soft goods and fabrics, but it's actually around, okay, where are we pushing and pulling on the body? How can we reduce shear stresses? What are the kind of places that we can apply force that works for every body shape and size, which is another big leap from, you know, what worked on our initial team of 5 people did not work when we started looking at, you know, 300 or 400 people, kind of the representative of our customer group, different body, different shapes and sizes, very challenging. What works for long-term usage, right? So again, as we got feedback from 3 or 4 months of use, places that we thought would have been fine before, people were getting hot spots and it was a real issue. And then things like comfort around thermals and like sweating is actually a big one, right? So especially in summer, you know, anything that would kind of move the body so you're tight on the body can also be kind of thermally uncomfortable. So we look at a lot of very breathable meshes and kind of taking a lot from the outdoor industry and, you know, backpacks and things like that, which are designed to kind of apply load but also be comfortable at heat. And so that's kind of the direction that we've now headed in. I still think there's a huge opportunity for more kind of true smart garments, let's say, than what we're doing. And I think the big opportunity is probably going to be around balance, because something like that is, you know, you need high bandwidth actuators, but in principle, you don't need as much force if you can use, you know, quick enough kind of sensing and intelligence to identify when someone is becoming unstable and provide small corrective measures. But to do that, you also need like multiple degrees of freedom. So it lends itself better to, you know, a garment that's made of a collection of, let's say, smart fabrics or smart actuators, or, you know, or even kind of Bowden cables, but with some flexible adjustment points. So I think there's a huge opportunity there if we can if we can get there. And so I'm excited for the technology to get to the point where we can start to think about what it would look like at a commercial scale. Yeah.
That's so helpful. The practical perspective, the user-centered design, and all of the real-world issues are so much appreciated. All right, let me just remind everyone who is watching the webinar that you can start to put questions into the Q&A now using the Q&A feature of Zoom, and then we'll go through those at the end of the introductions. So next up we have James Cotton. James is an MD, PhD, an electrical engineer, a neuroscientist, and physiatrist at Regenstein Foundation Center for Bionic Medicine at the Shirley Ryan Ability Lab in Chicago, and he's an assistant professor at the Northwestern University Department of PM&R. And his lab works at the intersection of many topics from AI and wearable sensors to biomechanical modeling and technologies to monitor and improve rehab outcomes. So James, looking forward to hearing from you.
Yeah, thanks for the opportunity. Yeah, so I mean, as you kind of heard, I'm both like a clinician and a researcher, and do a lot of work kind of wearable sensors, computer vision, and I kind of like what Paula was talking about. Like, I'm really focused in measuring real world function. Like, as a clinician, like that's the end goal. That's what we're trying to do. I really appreciated the comments on usefulness, because that is what actually makes things be used, right? And kind of along that, I want to start with a bit of a provocative statement, kind of reflecting on my clinical experience in rehabilitation, which is that essentially no technology is like meaningfully gotten out into real world use that's much more advanced than like a multifunction grasping tool or like an orthotic. And I guess the only exceptions would be prosthetics and power wheelchairs, right? But otherwise, there's a lot of really exciting and interesting things, but nothing that is close to standard practice, nothing that has the evidence of effectiveness to where we actually do this routinely. And so I think, there's been so much potential, but there's also been so many like missed opportunities. And that's why I'm so excited about these kind of concepts around like next kind of generation assistive fabrics. And so, the kind of combination of a core technology that integrates better sensing, intelligence, and actuation could just be an enabling technology across a wide range of things. And I think it's a wide range of things that we currently try and do poorly. So for example, take sensing, right? So I say this as someone that develops wearable sensors in my lab. They don't give us the kind of insights we want into the real world, right? And so like, for example, Paolo was talking about some of Kathleen Lang's great work, right? But I think there's a real risk where you take accelerometry data at the wrist and try and extrapolate what someone's doing, and you miss things that would matter to me a lot clinically, right? So like I do a lot of toxin injections to adjust hand function. And often what you end up having is someone that gets their hand to the point where they can like open it a little bit and they can wedge things in there, and it meaningfully allows them to do bimanual tasks, but it's not going to show up in that kind of crude measurement that we get from accelerometry. And we actually run the risk of interpreting that as evidence of absence of improvements, when really it's just an absence of evidence, and we need better technologies to measure things in the real world. So you can imagine a smart glove that actually has integrated EMG measurements and really looks at like the, and strain measurements, and looks at like the postures of the hand and can measure this at scale. I do a lot of work in computer vision because I think it can actually allow us to measure these things more reliably with current technologies. But the limitation of computer vision is compute intensive, and you can only do it where there's cameras around, right? So like this kind of technology could give us the insights we need into real world function. And then the ability to bring actuation into it, coupled with this intelligence, right? And I think you were talking about that with the kind of subtle controllability and what you need to be able to do, and when you need to be able to do it. It's huge, but the space is so big, right? And we have so many principles we can build across. So like, for example, in orthotics, right? We talk about the distinction between an orthotic and a therapeutic or an assistive technology. And so like these kind of technologies, we can really think about them in those buckets, right? So like you could imagine some kind of bracing system that like variably stiffens, right? Which is essentially an advanced version of an AFO, right? Where it can be manipulated so it can flex in certain directions but stop other movements. But like this can now actually be dynamically modulated based on the activities that someone's doing, right? Or you could start to actually produce positive energy in there and give them some assistance. Which then you can get really intelligent about where you do it. And so like one of my colleagues, Jules DeWald, has done some great work that just providing the only example really that they found where robots are helpful therapeutically is if you provide a little bit of sometimes a lot of anti-gravity support, you reduce the reticulospinal drive and you allow someone to increase their corticospinal control, relative corticospinal control, and increase their workspace, right? So like if you could actually produce a wearable shoulder garment that just intelligently provides just that one joint, you could really improve where someone could get their arm. And so, yeah. But at the same time, also, we need to learn from the failures of the current technologies, right? So ease of use, reliability, simple donning and doffing. These are, the majority of rehab technologies just end up in someone's closet, right? And so like, these are things that need to be like first and foremost. And again, the benefit of fabrics is we have a pretty good many billion person case study that proving that people routinely will put on and off fabrics on a daily basis, thankfully. And so I think that's a really exciting kind of opportunity, and I'll stop there.
Thanks so much, James. So we're going to go to David Rinkensmeyer next. David's a professor at University of California, Irvine, has appointments in mechanical and aerospace engineering, anatomy and neurobiology, biomedical engineering, and physical medicine and rehabilitation. So his research activities focus on movement control, neurorehabilitation, and robotics. And let's hear what you have to say. Go ahead, David. You're muted still, so.
Okay, slides okay? Can you see that?
Yes, looks great.
Okay. So I'm gonna talk about a couple of things that have been commercialized. So I have a financial interest, but I'm gonna talk mainly about people with stroke. So this is a short movie of someone trying to lift their arm and up. You can see the struggle there. And so the question I wanted to ask is, if you're talking about assistive fabrics, like why would you want to assist in movement for rehabilitation? What's the point of that? And it's actually a pretty debated thing right now, but I want to show you, it might be point like assistants can do numerous things. Some of them are good, some of them are not so good. And I'm going to show you one thing that I think is a really helpful thing. So here's an assistance machine, kind of like an assistive exercise machine that we invented in the lab called T-Rex. Basically, it's rubber bands and a grip support and some games. And if you do this, you recover better than if you do conventional sort of self-supervised exercise. And people find that that type of device very motivating. They like the computer games, they like the feedback, but also one of our participants said this very revealing thing: if I can't do it once, why would I do it 100 times? So assistance machines enhance motivation. So that's a good reason to use assistive machines. So that became a commercial product. So I think I thought James was maybe too severe on like devices aren't out there. Like, so I ran a quick calculation. There's 1,500 there, it costs $60,000. And I think there's probably conservative been about 500,000 people have used it based on my kind of estimates about the average usage at facilities. And this is a recent clinical trial from India showing you get about 55% better arm recovery if you add that on to the conventional training. So we checked that idea that assistance is more motivating with this robot. Assist you in playing Guitar Hero. And if we assist you at a high level, so you get 80% success with the notes versus at 50% success. These are two groups of stroke patients, and we asked them to rate their motivation for the training right after they did it each session. You can see it's significantly higher. And if you turn off the robot, they can only get about 20% success. So that's very demotivating. So we've also made fabric-based sensors, they definitely make it more accessible. So this is a device made by Flint Rehab called Music Love. It's a company I started with, helped start with former students. It's about 10,000 users here, and we've logged, millions of movements anonymously back. But the problem with this is we found only about 13% of consecutively admitted stroke patients have enough hand function to use that. And we really found that with the company too. When people were crawling, only about 1 out of 8 people could have enough hand function to get it. Now, interestingly, Quentin Sanders, a former PhD student, he looked at, so in the Music Lab, you get to titrate your game success, like the rate the notes are coming and the number of grips. And basically what we found is people, they change the settings about 10% of the time, And they do it in a way that sort of zeroes them in on about 85% success. So most people like to train at 85% success level, and they do sort of the wise thing to get themselves there. Similarly, so at Flint, we made another device for people that had more impairment. You can do about 40 exercises with these pucks. This is, again, about 10,000 home users now with it. But we looked at a big data set of 2,500 people. And what I want to show you here is this one, the software sets the sort of difficulty for you. And if you have 100% success, you stop using it really fast. So this is the probability that you're going to get up to 5,500 reps. And then if you have low success, you don't use it as much. And then if you're at this 90% success, you seem to use it much more. It's like an optimal success rate. So yeah, so I think why assist? It's a complex thing, assisting people for therapy. But one of the things it does is gives people better agency. And what we're finding is that better agency, the success of moving, seems to motivate longer term training. Like people are more likely to engage in it in the real world. And I think with fabrics, you could do that at scale. Like potentially, you could do that at scale to create better accessibility.
Terrific. Thanks so much, David. And you're, really highlighting in your discussion, differences between assistive technology for the purposes of rehabilitation and recovering lost sensory motor function, as opposed to assistance where you're just trying to help someone do a task and you're not actually worried about some kind of therapy or recovery.
Right.
So I think we often just use the word rehabilitation very generally,
Oh, right.
But in David's point, he's speaking about using it as a way to enable therapy, whereas others may be using it as a way just to describe any sort of recovery of function, even if it's not recovery of independent function in a therapy sense. Great, let's move on to last but not least, we have Connor Walsh. Connor is the Paul Mader Professor of Engineering and Applied Sciences at Harvard School of Engineering and Applied Sciences and an associate faculty member at the Weiss Institute for Biologically Inspired Engineering and an adjunct associate professor in the Department of Physical Therapy and Athletic Training at Boston University. And he runs a very interdisciplinary lab that brings together engineering, industrial design, apparel, biomechanics, physical therapy, and business to develop and translate disruptive robotic technologies. Go ahead, Connor.
Yeah, thanks, Alison, and thanks for putting on, to all the organizers, putting on a nice webinar. I enjoyed the other talks as well. So my name's Connor Walsh, and I'm going to just give a little bit of an overview of some softwareable robots that we've been working on for a variety of different applications. And then as part of the discussion, happy to go into more detail of some of the challenges and also future opportunities kind of like in this area. But I thought that just let me advance the slides. I thought I'd start by just showing kind of where we started, because it's always interesting to look back before you think about kind of going forward. So this was about like 10 or 12 years ago. You can see we had these kind of pneumatic ankle exoskeletons that were using these inflatable artificial muscles, to try and apply ankle plantar flexion torque. And then we had this soft robotic glove with MUNET actuators, to try and kind of help with opening and closing of the hand. And for these projects, we definitely learned a lot about, I think we convinced ourselves that this was a promising area, I would say, is what we did. Before this, we weren't really sure, can you interface to the body with apparels and textiles and still apply sufficient forces? So neither of these projects are particularly impressive in terms of their results, but I think they kind of gave us the confidence that, this was an area that was interesting to work on. And then the other thing I'd say, is that you often have to start somewhere like this with the roughest crude prototype to try and understand like some of the human factors aspects of these types of systems. And then from there, really think through what are the ideal requirements for your actuators, for your sensors, for your human interfaces, to then understand kind of how to move ahead on the engineering detail kind of design phase. And because we wouldn't have been able to predict what some of those were without kind of building these first crude prototypes and trying things as well. And so this is kind of our space. You can kind of see it's actually our old lab, but a time lapse. So we have like apparel designers working alongside, movement scientists and physical therapists working alongside engineers and roboticists. And it's really kind of those different disciplines working together that's like really critical kind of like for this field, based on our experience. And then we iterate a lot. So we do a lot of iteration. with humans in the loop, and they can be end users or just members of the lab. And then eventually we kind of freeze the design, and then from there, kind of like do more rigorous testing. So a few projects that we've worked on, we've tried to augment healthy human performance. So can we help people walk and run more efficiently with soft-wearable robots? And we had some nice papers that kind of like highlighted that. We use more traditional actuation approaches for this. I agree with some of the earlier comments. I don't think some of the more novel material-based actuation approaches are quite ready. And we use kind of cables as a way to apply forces kind of to the person's body. And for most of our applications, we try to keep the weight close to the person's waist and center of mass, just because that's where there was less burden. And then we thought about how we would kind of use the same technology for restoring function. And so here again, we're using apparel to ankle distal and proximal to a joint, and then we're using flexible cables to transmit power. And so we can kind of locally apply forces at the ankle joint, in this case for a stroke survivor. And then the key thing about these technologies is you want them to be transparent and to get out of the way when you don't need the assistance or you don't need the help. And I think that's kind of a key advantage of kind of like textile-based wearable robots, is they can kind of really disappear when you want them to be powered off. We've also kind of thought about augmenting healthy individuals in terms of like not reducing reducing the risk of back injuries, rather than kind of like improving kind of productivity or performance. So we kind of developed a back exosuit that spans the back and the shoulders, the shoulders, the back, and the hips, and basically kind of applies forces in parallel with the back muscles, which during lifting have really, really high, like thousands of newtons of forces on them, to kind of try and take some of the strain off that tissue and reduce the risk of injury. So we think this is cool that you can see here. This was actually kind of a prototype that we made before we spun out a company. So Verve Motion is a company that's now commercializing this. So workers are wearing these devices in industry. And this was a prototype we built before the company spun out. But you can kind of see here, the person's wearing a robot. So it has sensors, it has actuators, but it doesn't look like they're moving like a robot. I think that's kind of one of the unique opportunities for kind of these types of soft wearable robots. And so every time this person is lifting, the device is detecting that the person is lifting. It's applying forces during the lift in a way that's customizable by the user, and it takes about 40% of the strain off their back, is what we've shown so far. And then the last thing I'll just highlight is, like, most of those previous approaches are using kind of electromechanical actuation approaches. We do think there's a place for pneumatic-based systems. I think there's still work to be done to make these systems practical, but it's definitely an active area of research in our lab. So Alison's group has done some nice work as well, like using inflatables for the upper extremity. And I like the comments about providing anti-gravity support to the arm and to the shoulder. I definitely think there's a lot of potential there. So we're kind of working on these soft inflatable wearable robots that can provide anti-gravity assistance to the arm. And we've also played around with the elbow and the glove. And so here's just a couple of videos on the next slide. On the left is a glove. This person has hand impairment. On the right, this person has arm impairment. And the first part of the right video is no assistance. And then the next part of the video is basically the device providing some amount of anti-gravity support and allowing this person to leverage their residual capacity and then be able to kind of perform that task better than they otherwise would be able to. So I think I'll end there just acknowledging there's like lots of people that have contributed to these projects over the years, like many past and current lab members. And I showed the videos at the start just to kind of show where we started. And oftentimes it's okay to start with crude, rough prototypes, but over time with a lot of smart people, and I think you really can make these technologies practical and better. So thanks.
Great, thanks so much. I'm going to start with some questions that I had, and then we'll go to questions in the chat or in the Q&A, the Zoom Q&A. Many of you mentioned about the existing technologies, especially for actuation, but maybe also for sensing, also not being quite there yet. So I'm curious, are there recent technological breakthroughs in sensing or actuation that have kind of captured your interest that you think are not ready now, but maybe with the right research, the right level of investment, that maybe in 10 years it might be applicable? And just a couple thoughts to kick things off is that I might have missed it, but I'm not sure if anyone mentioned AI, right? And this is not a community that really focuses a lot on artificial intelligence and autonomy, but what are ways in which AI might be used in terms of smart materials or smart actuators, hazels? Are there other types of actuation technologies that you think, if someone just put the right focus on it that we could get there. So yeah, if anyone would like to answer what are ideas of things that you've seen that you really think need more investment? And maybe I'll start with James since he's so politely raised his virtual hand.
Yeah, I guess, and I partly was thinking about this, and then when you said the AI, I decided to lean into it. But I think like high density EMG as a recording modality is really, really tempting, but very far from scaling right now, right? The adhesives, like a lot of skin prep, the very expensive adhesives. But like that, the kind of success story I want to point to is, you know, Meta with their Control Lab acquisition, they like, you know, they recently had, David Cecilio had this paper on their massive data scaling for their wrist-worn device, where they, you know, kind of took a data-driven approach to hand gesture decoding and something approximately resembling like high-density EMG decoding, which is, again, normally a process that takes you know, a huge amount of compute and offline processing, and they kind of train a network to approximate this, and you kind of put this device on and it instantly can do grasp recognition, even on a part of the arm that's not optimal for the anatomy. And so I think that's a kind of a success story of both like putting the right product design in place and using some AI to make something that's robust. At the same time, there's no evidence that would generalize to people with movement impairments. And, you know, I think we'd want a sort of fully wearable equivalent of that could just be like flexibly applied all over the body, in my mind.
Great, awesome. Let's go to Paolo and then Catherine.
For the AI component, I would echo what James said, and I've seen a huge impact on our ability to actually make sense, clinical sense of data that we're collecting with sensing technology in the field. And it's truly across the board. It's not purely just advances in machine learning algorithms to process accelerometer data. It's even generating annotations of the video recordings that we have, things of that nature. The change has been dramatic. But the other thing that James alluded to is the interaction with the technology. That's an area where, you know, one of the things that we discussed prior to the meeting, kind of offline, Alison, right, is that what we would really like to see, right? And so, in some of the technologies that people are exploring, such as, you know, a colleague at WGU, right, is using ultrasound for that, right? And so Connor is involved in some of the work with Lua Wad on recordings and stimulating muscles, right? And so there are at least two groups at MIT, hers, and in Pisa, Chris Cipriani. They're doing actually beats to record the activity of muscles very accurately and in depth. And that allows them to do, again, what James alluded to, improve the interaction between the subject and the technology, right? So to use a term that a colleague and friend likes to use, we would like the system to be more symbiotic with what the subject is attempting to do, right? So a typical, very super easy, practical problem that we have, right? And so is that to get this system to assist gait in steady state conditions, we need multiple steps, right? And so it can be even a couple of cycles. But if we're using the technology to decrease loads on the anatomy because we need to protect it, because we don't want to allow on tendons and ligaments standard loads, right? And so even a couple of cycles are really not going to be good, right? And so can we make the system actually do what the patient does want to do? And I'll let Catherine go.
No, I think just echoing what James and Paolo were saying, the sensing I think is very promising. So there's a huge variety of like truly e-textile based sensors that are sort of very nearly ready. I think the actuation much less so. But to answer specifically the question about how AI can help, I think one thing it can start doing is compensating for some of the challenges associated with the like emerging soft actuation modalities. So one example of this is like how you attach to the body. If you're trying to use a garment, like everyone's garment sits in a slightly different place, it's much harder to get true joint alignment, etc. But you know, already even for some of our systems, we can use AI to do like a quick on-body like recalibration, kind of seamlessly readjust everything to kind of fit a new person who's wearing a garment in a slightly different position. So I think there are examples like that. I think similarly, some of the challenges around soft actuators being too slow and low bandwidth, if you can start using AI to be anticipating movements further and further into the future, you can kind of get away with less responsive actuators for a longer period of time. Or again, like taking up slack kind of in your system preemptively so that you can improve your responsiveness when it actually comes to it.
Thanks, David.
Yeah, I was just going to mention, we have a project with the AI side of things. I mean, one of the questions is just like, how do you find devices? Like if you're a person that needs rehabilitation, and it's really, really difficult. It's very arbitrary. So we're trying to make like a chatbot that can help people find devices. So we found about 60 devices under $10,000 for rehabilitation therapy after stroke, basically. And we asked, so we have a paper in ICOR on this, but we asked, what do you want to know about these devices to a group of therapists and stroke patients? And they gave us sort of the things they want to know about. And then it was very difficult to get that information about the devices off the web or directly from the companies by email. So anyway, I think there's an opportunity for AI and just like increasing uptake of devices, like helping people connect to things that might be useful to them, because right now it's just so arbitrary in the way it works. So
Yeah, that's a great point. Access is a huge problem. Maybe I'm going to switch over to some questions that are from the audience, and then we can go back and have a quick lightning round of last points that everyone wants to make. So we have a question in the Q&A from Steve Collins, who's a mechanical engineering professor here at Stanford. I'm sure many of you know him. And he's asking about interest in devices to address joint loading and prevent pain and injury. And I think Connor addressed this a little bit with his last example, or one of the last examples of working in a facility where you have to lift heavy objects. And maybe I'll just riff on Steve's question a little bit, which is that with some of the approaches, if we're planning to use relatively soft materials and soft actuators, you might actually increase loading on joints. And so maybe devices can alleviate, but if they're not designed correctly, I'm always concerned that maybe we'll increase the joint loading in negative ways. Connor, do you want to take that first and then see if anyone else wants to chime in?
Yeah. Nice question, Steve. Hi, I guess can't see you, but hopefully you can see me. So I think how you apply loads to the body through any type of wearable robot is important. I think there is often this kind of conception that if you apply, a force, across a joint, you're increasing loading on that joint. But I think it really depends on how you're applying that load. So, for us, we're applying it kind of like further away from the joint than the biological muscle is applying the load. And most of the loading on joints comes from biological muscles. With the back, you've got 4,000 newtons applying loads at that joint, which is what leads to injury. So if you have a moment arm that's like, 5x or 10x that, if you're applying a smaller force, you can still have a pretty big moment, assistive moment kind of on that joint. And so for us, we've done some work in simulation and also experimental, where we've kind of like either simulated or measured kind of like loading on the joint. And I would say that it does change kind of like the direction of loading a little bit, but the majority of the time it's unloading the joint by applying these external loads. So we have a project that we haven't published yet. We actually did it pre-COVID with Charité in Berlin, where they had implants instrumented in the hip joint, where you could measure the joint loading, and then we applied forces with our exo, and we saw reductions in joint loading by applying those forces. And so I think just really kind of digging in and looking at the mechanics and thinking about like how are you applying those loads. So I think exos have the potential to unload joints. Short answer to the question. I would say it's an interesting area, but I don't think the changes are huge. And I think sometimes there can be small increases, but I don't think they're kind of very large increases. And they're probably no more than would be typical. They wouldn't be as much as the difference between going for a walk and going for a run, for example. Like if you go for a run, your joint loading is going to be way higher than if you walk with an exo. And that's another way of thinking about it, I would say.
Thanks. Let's do Paolo and then Catherine.
I have just a brief comment. When we use this type of technology clinically, it is essential, the sensory technology piece that I mentioned earlier, right? And so because what Connor said, it's 100% something I would agree upon. except that in patients, we do observe co-contractions of agonist and antagonist muscle. And so you have to be extremely careful with that. And Steve, I'm going to say for the rest of the team, because Steve is aware of it. As I visited Scott Delp, I visited Steve's lab, who is phenomenal, by the way, very beautiful lab, Steve. And he knows we have been using I'm sorry, Luke Mooney's technology out of MIT to help with plantar flexion of the ankle during gait. And we have shown using both OpenC models as well as the MyoSuite type of musculoskeletal modeling that we get a significant decrease on the load on the Achilles tendon, which is very important in tendinopathies, for instance, right? And we're doing the modeling because we're also looking into medial lateral stability, and we want to get into ligaments that you really don't have access to like you would have for the Achilles tendon, right? But in a clinical study that we didn't perform, it was performed by the colleague in the military, the technique was used, attention was really put on making sure the patient was careful at being in sync essentially with the system and avoid the co-contractions. And there is a communication that I'm more than happy to share with the group here that a physician colleague in the military did, in which they show that they can actually shorten the recovery process, even in a fibula fracture, right? By actually replacing the stabilization that you do essentially with immobilization in these individuals with dynamic support using an exoboot, right? So with caveats, this is actually of fundamental relevance from a clinical standpoint.
Thanks, Catherine.
Hey, Steve. To answer the question around what are people interested in using it for, injury prevention, consumers have no real interest in, or like a passing interest, but adoption after a month or two for injury preventive devices is like too low, I think, for this kind of intensive technology. But it's exactly the place that we've seen traction on the enterprise side, right? Like, because if you can show that you're reducing workplace injuries, like that's why, Connor's talking about Verve, there's like a few other examples, where there's a real business case and you can get a single B2B customer to buy technology from you. Like that's exactly where I think you'll see, these technologies first adopted. And I think an interesting space for soft exoskeletons in particular, or kind of smart textiles, are going to be environments that are less like warehouses and logistics, where you want kind of higher force applications, and more like nursing, where the nursing workforce is getting older. A lot of them will have joint injuries and are dropping out because of injuries. But hospitals are very incentivized to keep them there, but they need something that's low profile, that's subtle, that's, more appropriate for kind of that setting, as opposed to maybe industrial warehouses. The reverse is true. So on the consumer side, knee pain in particular is like the #1 thing people keep emailing us about every single day. And it goes to something that David was talking about around a lot of these people are kind of confused. They've tried something, they've had braces, there's like a variety of solutions out there, and they've often tried a number of things or been to several different doctors, but haven't found anything that quite works for them. But that's like, if you live with pain every day, I think this is incredibly motivating. So that's the group on the consumer front, where the strong willingness to try almost anything that will work, but at the same time, people are kind of becoming a bit disillusioned sometimes with mobility aids that haven't helped them a lot in the past.
Can I just ask a quick follow-up question to that? So when you made the comment about the lack of adoption for injury prevention, right? Like, so like when, for example, falls, second leading cause of, injurious death. And so obviously fall prevention has a huge health impact. Now, you kind of alluded to the problem with injury prevention is lack of maintenance of the use of the technology, right? So like in theory, if you actually could make this easy to use through the kind of division of assistive these fabrics, right? Like the barrier you presented, if I understand it, would go away.
That's true, but I think it has to be so easy to use that it's almost equivalent to an existing garment. And that's such a high bar that it kind of feels unrealistic where we are. But yes, in principle, if you can solve that problem, yeah.
Good goal.
So there are a few questions in the Q&A that I won't call out individually, but it's folks who are just really leaning into what are the actuator technologies' current limitations and what is the promise for certain actuator technologies. So I want to push on that a little bit more. Like, Connor, what exactly is missing in pneumatics For those of you interested in e-textiles, what are exactly the limitations, and why not Hazels or some of these other actuators? If anyone would like to chime in on those.
I'll give my quick thoughts. I think pneumatics have potential for situations where you need to push rather than pull. I think electromechanical systems are definitely pretty good with cables at pulling. And I think, if you're applying torques at a joint, you can apply torques bidirectionally. But for situations where you want to push, I think pneumatics have potential there, I would say. And then I think you mentioned Hazels, and Allison. I think Hazels are pretty cool and, kind of core technology. And I think there's a lot of potential to build on that.
Great. Any other thoughts about specific actuator technologies? Okay, and then let's take another question about the interface with the human's intent. And we talked about AI and measuring something about the world and their desired activities. What about brain signals, like neuronal signals, to increase performance? Is that anywhere people want to go? Crickets.
Oh, sorry, go ahead. No, go ahead. You got it.
Well, I was just gonna, people have been trying this for years. I'm sitting here. Here's a 65,000 channel, fully wireless brain machine interface chip, right? So hopefully at some point these kind of technologies really get out there at consumer scale. But non-invasive technologies don't work well, and the body already formats so much information that's usable, whether it's in the format of EMGs, kinematics, or even voice commands. And then you've got all this work going on in foundation models for robotics, right? Where you have these things that can really infer intention at a wide range of tasks that I don't think they've quite been adopted into the rehabilitation domain. So I think it's just going to be, I don't see that as being the technology that's even for assistive robotics that are currently targeted for BCI. I think the place we're going to see those get into real world applications is going to be language control well before it's BCI based, as someone that does BCI work. I say that.
Great, thanks. Paula?
David, I think you had something to say first, David.
Oh, yeah, I'll say it real quick. It was just that I think the spinal cord stimulation stuff is an interesting thing because it sort of boosts up the ability to move again, but you're still in control of the movement, but it's sort of boosting up it's almost like putting on an exosuit or something like that, right? It's with that, and it has perfect knowledge of your intentions. So it's kind of an interesting, so maybe incrementally, if you get the spinal cord stem plus some sort of exosuit, then you get double the benefit or something. So I thought that's something interesting.
So Alison, if I could just offer a very super brief comment. When we think of interactions or interface with the nervous system, I think the brain-computer interface makes sense for individuals with a spinal cord injury, but we should really think of the nervous system as a whole, and there are lots of opportunities throughout the nervous system to interact with the body.
Great, thanks so much. So let's just see if there's any burning points that anyone wanted to make in maybe less than 30 seconds a person. Feel free to put it out there now. If you don't have one, I'll just put one out myself while you think about it. Donning and doffing, getting these things on and off the body, especially for people with impairment in movement. There's a really nice result out of KAIST recently of this giant exoskeleton that could attach it to someone else's body. This is in Korea. But how do we do that now with these flexible, maybe more floppy devices is a big challenge. Any other last points people want to make?
So if I could, just as a Spalding, and I guess James might have the same request. So, we're talking to a community of technology people who do fantastic work in soft robotics. Give us something that our patients can use in the home setting effectively. We really don't need, at least in my opinion, I don't know what your thoughts are, James, right? So we don't really need exoskeletons to get our spinal cord injury patients to walk in the community, right? It's great if they do, but it's so inefficient. But if we could get something that actually works in the home setting, that would be absolutely phenomenal. And there is such a lack of research in that area. That would be something that we would adopt tomorrow clinically.
Okay. Any last burning points? If not, then I'm going to conclude this webinar. I want to thank you all so much, Paolo, David, Connor, Catherine, and James for joining us and having this discussion. For folks who are tuning in, please note we have another one of the series in this webinar next Friday, and then we'll have another one the Friday after that. So we have links to register for those in the chat of the webinar, and we will have a recording of this posted later. Thanks, everyone.